say a few words, really not many. So one of the goals of this workshop, what we wanted to do when we organized the program, is to give you a picture of modern machine learning, both in its diversity of programs and approaches. So we will see many things during the week, from neural networks, reinforcement learning, bandits, unsupervised learning, all of those things. And also in terms of approaches, there will be some complex geometry, probability, optimization, all of this. And we'll start with PeterBartlett, who will tell us about representation, optimization, generalization, so everything coming together for deep networks.
Thanks, Sebastian. Thanks for inviting me. I'm really happy to be here. So I want to talk today about a few properties of deep neural nets. And I guess they need no introduction. They've had these huge successes across a whole range of application areas. So I like to think of them as compositions of many nonlinear functions. So we can think of computing some function h by taking a composition of a bunch of vector value functions. For instance, each one might correspond to a linear function passed through some component-wise nonlinearity, like a sigmoid, if you're old-fashioned, or the modern way, is a piecewise linear nonlinearity, or some max pooling thing, right, which takes a vector input, and for each output there's some subset of the inputs, it returns the max of those. All of these are Lipschitz maps from one vector space to another. And so these are the typical kinds of parameterized functions we're considering compositions of. But just abstractly, I'd like to think of it as a composition of vector value functions. Okay, so why would we study these things? Well, the claim, and I guess why have certain instances been so successful? The claim is that somehow they're learning useful representations, and it's a rich non-parametric family of functions for doing that. So the representation learning idea is that experimentally you can observe in a vision problem, for instance, as you move from the input of this network towards the output through these different layers in this deep composition, that early on you're computing, if you look at what these things are maximally responsive to, early on you're computing very simple features like edges in particular orientations, and later you're computing something that's a combination of these things, getting progressively more complex. That's the argument at any rate. And as a way of parameterizing functions like this, depth is somehow providing us with a parsimonious way of representing these functions. So the approximation theorists have known for decades that we can get much better rates of approximation with nonlinear functions, with nonlinear parameterizations than with linear ones. And you could actually come up with, there's been quite a bit of recent work, you can actually come up with specific functions where you can show, to represent the function in a composition of a certain depth is somehow easy. Go to something that's a shallower representation, and you need exponentially more complexity to represent those. So the depth is certainly providing us with something in terms of how rich the functions are that can be represented with a small number of parameters. But both of those things should give us some cause for concern. So with the optimization question, a nonlinear parameterization is something that we might expect to cause problems, and apparently we should think of it as likely to become worse as the depth increases. And if we have a very powerful way of representing a rich family of functions with few parameters, then again we should be concerned about the statistical consequences of that. What's the complexity of a deep composition of this sort in terms of its generalization properties. So they're the things that I want to talk about. I guess that's the motivation for the three things I want to talk about today. Maybe it'll be only two things. We'll see how we go. The first is looking at some representational properties of a family of deep networks called deep residual networks that have become very popular in computer vision problems. So we'll look at some properties of these classes of functions. That suggests a particular style of regularization that should be useful for optimization. And so we'll look at some results about optimization in these networks. To do that, we go to the kind of simple case where we remove the nonlinearities and assume that we're taking a composition of linear functions, okay, which is, you know, a crazy thing to do because a composition of linear functions, of course, is a linear function. But in any case, we'll see that the optimization questions are already non-trivial in that case. And we can get some insight there about what we can and can't do with simple gradient kinds of methods. And the third part of the talk, if we get to it, is looking at statistical complexity of these deep networks. So looking at a way of measuring the complexity of the class of functions that's computed by deep ReLU networks and how it relates to some dramatic generalization failures that have been observed empirically. Okay, so for the first part, I want to say a little bit about deep residual networks. So here I'm borrowing some slides from Kai Ming-He's ICML tutorial from 2016. So this graph is showing the performance. The bar graph is performance on a particular benchmark. This is a image classification problem. And looking from right to left, these are the winners of this competition each year from 2010 through 2015. You know, smaller is better. This is top 5 error, the bar graph. And you can see there are 2 big step changes there. One when things switched from using, you know, hog and sift and these specific features with linearly parameterized functions to deep nets, where deep meant 8 layers. And then there's another big step change right at the end when, which corresponded to the shift from deep nets to ridiculously deep nets. And, you know, this is a sequence of slides that is supposed to impress you with just how things changed over that period of time. Okay, so you know, these residual networks had 152 layers at this stage. I mean, people have considered even deeper networks. So what's going on here? What are these deep residual networks? So in a standard network, we might think about, let's say, a ReLU network which has this piecewise linear nonlinearity. Just think of what 2 consecutive layers in the network would compute. We take a linear function of the input and then pass it through this piecewise linear nonlinearity. Another linear function, another ReLU, and that's the function that gets computed with that composition of two layers. In a deep residual network, there's just this identity connection, right? So you can think of the function that's computed here as the input plus some nonlinear function of the output. So we're thinking here of problems like computer vision problems where, you know, the input is a vector of a certain size, and you want to compute something at every pixel of that input. Right, so there's no change of dimension. We're mapping from RD to RD. Okay, so in a residual network, we compute the input plus some nonlinear function, and that might be, for instance, linear function, nonlinearity, linear function. Okay, so it's these identity connections that make a difference apparently, and the claimed advantages are that you know, it's clear that if you have 0 parameters for this sort of network, the network is computing the identity function from end to end.
So the identity thing comes from the first to the last layer, or just?
No, this happens. So then these are stacked on top of each other. Okay, so each layer has an identity connection. If you have 0 parameters in here, then the nonlinear part is 0, and you're just computing the identity function all the way through these 152 layers. And you know, for 0, and typically these things are parameters are estimated using a stochastic gradient sort of approach that starts with small values of the parameters and works from there. And small values of 0 values of the parameters gives you an identity map in this case, and it gives you a 0 map in this case. And so, you know, we can think of those. That identity component of the mapping is providing useful feedback all throughout the network. That if the parameters are near 0, then the effect of a parameter early in the network on the loss that's seen at the output of the network is something that you can easily evaluate in this case. Things are well conditioned. Okay, and that sort of intuition is supported by the experimental results. So this is a 2016 paper that looked at this. On the left here is train and test curves as learning proceeds for a standard neural net that has the nonlinearities at each stage, and on the right here is for a residual network that has these identity connections. And they're showing, so the different curves down here is train and up here is test. The different curves correspond to different depths, depth 20, 32, 44, and 56. And you can see that the optimization is failing here, right? Because we know that in a depth 56 network, we can represent everything that you can represent in a depth 20 network, but we're not doing as well on the training data, and this corresponds to what happens on the test data as well. Whereas in the residual net case, you see the optimization is more successful on train and on test. You're seeing an improvement, and actually things improve as the depth of the network increases. This is going from, they're a little better separated up here, 20 layers, 32, 44, 56, about 110 layers, and things only get better in both train and test as you go to these deeper networks. So that supports this hypothesis that actually the identity connections are helping with the optimization. And in practice, as I said, these are widely used in computer vision. So there are various of these benchmark problems where using residual nets have led to big improvements over everything else. Okay, so what's going on? Let's start with some intuition that arises from linear networks. So this is work of Moritz Hart and Teng-Yu Ma. They considered the case where, throw away the nonlinearities and just think about a composition of linear functions. Of course, the whole thing is linear, but let's go with it anyway. So we think about a linear function that we're computing as a composition of linear functions. Of course, we can think of each one of them as just represent each one with a matrix. And the first result that they had is that if you've got a matrix that's invertible and satisfies its orientation condition, the determinant is positive, then you can represent that linear map as a product of linear maps that are all close to the identity. In the sense that the spectral norm of each of these differences from the identity goes down like 1 over m, where m is the depth of the composition. Right? So for a given linear map, you can represent it as a composition of things that are all close to the identity, and as the depth increases, you can make them closer and closer to the identity. So that's the first result, and the second result is a consequence for the sort of optimization landscapes that we see with these networks. So they made the assumption that you have a linear Gaussian model. So the conditional expectation of the output vector y given an input vector x is a times x plus some zero mean symmetric Gaussian noise. Okay, so under this model, suppose we represent the linear map that we want as a composition of m linear maps. Right? And we parameterize them as identity plus something. Okay, so this is our m composition of m linear maps here, and we would like to minimize this criterion, which is the expected squared Euclidean norm of the distance between our linear prediction and the actual output y, right? Which is linear plus mean zero. Okay, so that's the criterion. It's a quadratic loss. It's not a convex loss in these parameters a1 through am. Nonetheless, there's this very nice first order condition for optimality that as long as you keep all of these AIs, the deviation from the identity, small, right? Small in the sense that the spectral norm is less than 1, then every stationary point of this quadratic loss is a global optimum. So if you look at the gradient of the criterion here with respect to any one of these AIs, if that's 0, I guess I should say, if it's 0 for all of these AIs, then that implies that actually we've got the right linear function, right? That it's 0 only if the product of these is equal to A, the true linear relationship between X and Y. Okay, so that's just a first order condition, right? Every stationary point is optimal. You can't have local optima, you can't have saddle points once you exclude, once you keep things close to the identity. Okay, so the first part of the talk is looking at extending those results to the nonlinear case. So this is joint work with Steve Evans at Berkeley and Phil Long, who's at Google. So informally, the first result is a generalization of the linear case when we're talking about compositions of nonlinear functions. So we have a deep composition here, H1 through HM, and we're wanting to compute a smooth invertible map, H. And the result is that you can do that with a composition of size M in a way that keeps all of those HIs, right, in the composition, keeps all of them close to the identity. So just the notation here, this is the Lipschitz semi-norm, this is the smallest Lipschitz constant here for the function, for the difference between HI and the identity map. So this is telling us that as M increases, we can represent things with functions that are the identity plus something that can get flatter and flatter as the depth increases. So you can think of those HIs as being represented by an identity function plus some other thing, and it might be, a representation of this form, linear composed with a component-wise nonlinearity and a linear function.
Might be, or
it might be, yeah. I mean, so when we say that every smooth invertible map can be, I'll state the theorem precisely, I think, on the next slide, but when we say that it can be represented in this way, we're representing it exactly. In fact, you can construct the H1 through HM to satisfy these conditions. As long as we allow the number of rows of B, and so columns of A, to be as big as we like, then we can approximate that, any of those functions, however we like. Because, it turns out the construction gives HIs that are not just continuous, which, is good enough if this is not a polynomial, nonlinearity that's not a polynomial. It's not just continuous, it's actually smooth and invertible and, has all these nice properties. Inherits the properties of H. But it's important to realize, if you want to do this, you can't fix the size of this representation. I have a little more to say about that later on. Okay, so so this is the intuition. So let me say that a bit more precisely. Excuse me. So our function H, we're going to restrict to a bounded domain. We're going to assume that H is differentiable, invertible, and smooth. So the derivative changes slowly as you move around. And we're considering the induced norm here, the operator norm. So for some norm on the input space. Then some norm on this vector space. We're also assuming it's not just invertible, but has a Lipschitz inverse, right? So the Lipschitz semi-norm for the inverse function is bounded, there's this technical condition, we need a positive orientation. It's the same in the linear setting. And that's because we're wanting to keep things close to the identity, right? If you have, if the dimension is odd, then you know, we could negate things if this condition is not satisfied, and the same thing would be true. So this is just you know, the analog of the condition in the linear case. And the conclusion is that for a depth m, we can find m functions that represent h exactly on this bounded domain, and have the difference between that function and the identity is flat. Gets flatter and flatter as m gets larger at this log m over n sort of rate. Okay, so why is that true? I'll give you a quick outline. So without loss of generality, we can assume that h of 0 takes some particular value. Let's set it to 0, and that its derivative is just the identity. And that's because, you know, if that's not true, we can shift things, and we can do a linear transformation that ensures that you know, these conditions are true, and that shift in linear transformations, they can be done in a you know, small Lipschitz semi-norm deviation from the identity. Right? That's the linear result already. So let's assume that, and then construct this composition of functions in the following way. Make the first function, so a1 here is just a scalar. Think of it as a tiny scalar. So we're shrinking the x down, right, by a big constant factor. Then we're taking h at that near 0 value, and then we're blowing things back up, right, by dividing again by this small number a1. So as a1 goes to 0, this is just approximating the derivative at 0, which is the identity, right? So we have a map here. The first map in our composition is going to be close to the identity as long as a1 is nice and small. And then we just progressively, we're going to be computing maps like this all the way along, but with different constants. So the composition of h1, of h2 with h1 is going to be of the same form with a a2 that's bigger than a1. And we keep on going like that, getting these am's bigger and bigger, and at the end we want this composition of hm with hm minus 1 and so on all the way down to h1 to be equal to h, so we set am equal to 1. Right? And then the analysis is just, you know, if a1's small enough, we get the derivative at 0. We get something that's close to the derivative at 0, which of course is the identity. And if all of the ai and ai plus 1 are close to each other, then the hi that transforms from one to the other is close to the identity. And you know, that last part, there's a little bit of work in proving that, in that you have to prove things on two scales. So there's some detail to that. That's I'll sweep under the cover.
So the theorem is you're approximating h.
You're representing h exactly.
So
You're representing h exactly with a composition of these m maps
well, in a bounded domain.
in a bounded domain.
So there's a sense in which you're just sort of approximating sort of theorem around every point. What is h2? So h1 is approximating around 0. What you're kind of claiming?
So actually, you know, all of the slack here is in the analysis. We're representing h exactly on that bounded domain. Right. So h satisfies these conditions on the bounded domain, and we can represent it exactly as a composition of these m functions, and those m functions have this property that they're close to the identity in this Lipschitz semi-norm sense.
What was the role of the boundary domain? The boundiness of the domain?
So why do we need the bound on the domain? So when we're if you think of just that first so why is that essential in the analysis? So I guess at every step we're wanting to ensure that the perhaps with some additional conditions we could do without the bounded domain, but at this point we just say it's smooth, and that's enough to imply that the map on a bounded domain, the map's Lipschitz, and we need that. We need it Lipschitz in both directions. But I'm just trying to. I think we need it for more than that, but I just can't recall what's. Yeah, Sasha.
Can you pull out an approximate quantitative version of this?
Oh, a quantitative version, you mean instead of the big O?
Approximate. No, instead of exact approximate.
Oh.
Because it's interesting.
Yeah, so I guess the way we attacked it was to explicitly construct this sequence of n functions, and then just work out how close they all are to the identity. Is the suggestion that if we were to approximate the function, then somehow we could relax some conditions somewhere? Yeah, it's plausible. Other questions?
The dependence of the dimension, the approximation depends on the dimension?
No. It depends on the size of the domain. It depends on those Lipschitz constants, smoothness and the Lipschitz constant of the inverse, but it doesn't depend on the dimension. Right.
Is there a sense in how well the Hn minus 1 approximates the function?
Sure, because you can show that Hm is close to an identity, so you get, you can work out the notion of approximation in that. Okay. So we can get these flatter linear functions at each layer for a map of that sort, and then going on to this. Second result that holds in the linear case that you have just a first order condition implying optimality, we can get something of the same form in the nonlinear case. So here we're just fix a joint distribution on xy pairs, right? So these are vectors in Rd. The criterion we're concerned with is the squared error, so the expected Euclidean distance between h of x and y squared. And of course this is minimized by the conditional expectation, and you could think about this as, the results for any joint distribution, you could think about it as a uniform distribution on a training sample, and this is empirical risk, and we're wanting to identify the empirical risk minimizer. So the result is that if we've got a function that's a composition of m of these functions that are close to the identity in this sense, right? The difference between the function and the identity has a Lipschitz semi-norm that's no more than epsilon at each layer, then we can write an inequality that says that the functional derivative of this criterion with respect to any one of these HIs has an operator norm here that's bounded below by, think of this as just some number that depends on the setup here and the value epsilon, and multiplied by how far h is away from optimal, right? What's the value of q at h versus its minimal value? So unless, and I guess to be a little more specific, so we're considering a functional derivative here, a Frechet derivative. The norm is the induced norm. And so unless h is at h star, right, unless, I guess almost surely, unless the value of the criterion is the optimal value, you have a direction in function space in which you can move and improve.
So each has like exactly, you need some load on it and some property stuff, right? Like it has to be.
I'm sorry, you need.
Or something. Don't you need some kind of rule around H star?
We need to be able to work with.
It doesn't have to be a little curvy or something.
Right. So we're assuming that things are differentiable, right? We need to be able to work with this induced norm of the difference between H and H star. So let me go through. I'll show you. Actually, in a few slides. So we'll get back to it. So the theorem tells us that that if we have a suboptimal H, as long as we're close to the identity at each step, then there's some direction in function space in which we can move.
So here you have to assume that X was a bounded support? Otherwise you can't apply the theorem about H?
The theorem about H is not in the background as motivation here, because all I'm assuming is that the H's are close to the identity. But yes, this is the setting where you'd think, if I have the conditions of the previous theorem applying, then I can get something of this sort, where this is like log m over n.
Which would be an X bounded support.
That's right. And more severe conditions. That was assuming H was invertible, which is a strong condition. And of course we don't need it. We don't need it here. Okay, so every stationary point in this functional derivative sense is a global optimum. Okay, you don't have, again, it's just a first order condition for optimality. It doesn't say that you don't get local minima if you fix a parameterization and work with, a network of rows or something for each one of these HIs, identity plus, some restricted family of functions. I guess what it's saying there is that there's always a downhill direction in function space, but it might be that you can't find that direction with some fixed architecture, and we should certainly expect there to be local optima. There should be, I guess, stationary points that are suboptimal if you consider a fixed parameterization. There are explicit results of this form. I guess the message of the theorem is that this sort of local suboptimal stationary point can't arise because of interactions between parameters in different layers. It's happening just within a layer because you're restricting the class of functions that you're using. Just to say a little bit about this point, you can see that there have to be suboptimal stationary points for these sorts of parameterizations. So there are results from the 90s. So let's think about the sigmoid case, right? So we're thinking of these compositions as being identity plus some sigmoid network of a fixed architecture. There's a result of Charles Pfefferman that says that any network of this kind has a unique parameterization. So, up to the obvious symmetries, you can change the relabeling of nodes in the network. You can, modify the inputs and outputs by changing their sign. Up to those obvious symmetries, you have a uniqueness of parameterization of a function in this class, composition of these sigmoids. And that means, you could think about the y being given by a function in that class. So that's an optimal point in parameter space. And then go through one of these symmetries, swap a couple of the nodes around, there's another optimal point in function space. And the uniqueness result says that on the path between these two, you can't have a continuum of optimal points between the two. So, pick a path between the two and look at what Q does. And minimize the maximum value of Q on the path between the two. You've got to find a mountain pass somewhere that you pass through. That's a stationary point, right? And at that stationary point, you're suboptimal. Okay, so fix a parameterization, and you can't have this sort of first order condition being true.
How should you think of epsilon? Like if epsilon is log m over m,
it looks kind of bad.
because then the gradients are like.
Oh, right. That's right. So we get this log factor is sort of problematic. If you pin things together, then you're getting something that looks like we're losing at this kind of maybe polynomial rate as m gets better. Well, I guess another way of saying it is these results combined don't show that there's an advantage of depth. I think that's a fair conclusion.
Sorry, what about the use the first theorem, you need invertibility in your
Right.
Is that a reasonable assumption?
No, I think it's a strong assumption. So it turns out you don't need very much to have a function be, let's say, a difference of two invertible functions. Right? You can get by with some simple smoothness property to have that, but then this result goes away. Right? So yeah, it's true. We don't know how to extend things beyond this. Well, I guess I could tell you about one case where we extend things beyond the invertible. So I think I'm going to skip through the proof here because I want to get to the second part of at least two out of the three parts. So let me skip over the argument here. We can explicitly, just at a very high level, we can explicitly choose a direction in function space that gives us a derivative that corresponds to some constant times the criterion, a notion of the excess criterion, and the bound on that, the scale of that transformation depends on these parameters of the problem. Okay, so yeah, this question about invertibility. This is a strong assumption, and as I say, you can get rid of that if you're willing to work with, let's say, differences of invertible functions. But then the second part goes away. There are some restricted cases. So if you think of an invertible, a function that maps from Rd to R, if we can extend that to an invertible function that maps to Rd, then you can certainly represent that as a single component of a vector-valued invertible function. But yeah, we don't know of other cases beyond that sort of simple example. In the second part of the talk, I want to say a little bit about optimization in the special case of linear networks. There's a relationship to these Polyak-Joashevich function classes, and there are results for those. But here we have this constraint that things stay close to the identity. So, what about gradient methods that keep things close to the identity? So that's the second part of the talk, is looking at optimization when we're thinking of regularizing by keeping close to the identity. And we're looking at just local algorithms here, so things like gradient descent, perhaps with some regularization or projection in there. Okay, so this is joint work with Phil again and Dave Helmbold from UC Santa Cruz. So we're going to go back to the linear case and hope that we can get some intuition from results there. Of course, as I say, it's a crazy way to parameterize a linear function, right? As a composition of linear functions. So I've switched notation to these linear transformations now are matrices theta I, and we're taking a product of those matrices. We're going to assume that our xy pairs are distributed according to some distribution P, and we're going to look at optimizing a nice convex criterion like the expected squared norm of the difference between our linear map and y. We're going to make a few assumptions. The first one is that the input is white, and we could transform if it's not. This is not a big deal, it makes things a lot easier. The second assumption is that the y is linearly related to x, and that's without loss of generality because of the projection theorem. Let me go through the steps of that. So, if we just think of the least squares map as this phi, right, the minimizer of this thing, then we can write the squared error, just splitting it up into theta x minus phi x plus phi x minus y. The projection theorem tells us that if this is the least squares map, then everything in this linear space is orthogonal to that, or we could have done better, right? So the middle term goes away, and we just get a term that doesn't depend on theta at all. And obviously, if we're working with this criterion, we may as well work with that one and assume that y equals phi x. So that's the loss we define. So let's work with that case, just some notation. We've got f theta of x is this product of all of these thetas. So the capital theta, that's the subscript there, is the set of all of the matrices that parameterize our linear function. And we're going to write that as, the product from 1 to L. So theta 1 all the way through to theta L. So we'll use that notation. And then you can compute a simple computation to just see what gradient descent would be. So, okay, so we're starting off at the identity and then doing gradient descent. So updating each theta I in the direction of the negative gradient, and you can do the calculation. It looks like this, right? This is the difference between our linear function and the truth, the least squares one. And then, there are these linear transformations corresponding to the bit before theta I and the bit after. And eta here is the step size. Okay, so that's the gradient descent algorithm we're going to consider. And the result is that there's some constant and some polynomials, so that if you start out with the loss, this squared Euclidean norm below this constant, and you have your step size sufficiently small, then after not too many iterations, and depends only logarithmically on epsilon, you can get to within epsilon of the optimal. Okay, so this is without constraints on the true map, on the least squares map phi. I guess the only constraint is that it's that we start out with the identity map being not too far away in that sense. Okay, and the argument for this is that I guess getting something quantitative out of the proof of the result of Hart and Ma, you can show that if the smallest singular value of each theta I is bigger than 1 minus a, which is true if you're close to an identity, then the gradient is nice and big unless you're very close to the optimum. So that's good. We can also show that if we're close to the identity in the sense of having our largest singular value, not too big, then the Hessian isn't too big. All right, and then these two things together tell us that gradient descent is going to make lots of good progress, right? We have a decent downhill direction, and it doesn't change into an uphill direction too rapidly. So we make good progress with gradient descent.
This L theta was quadratic L theta, right?
L theta is quadratic. That's right. Yeah, right. It's a quadratic criterion, but it's quadratic in the product of the thetas.
I'm sorry?
It's quadratic in the product of the thetas, right? Theta L y blah blah blah. And there's an extra piece we need to do an inductive argument to show that we stay close to the identity. So the worst case spectral norm difference between a theta I and I is this quantity RT, and we can show it evolves according to, there's an inequality that says it doesn't blow up too much as long as you're not too far away from the least squares guy. Okay, so you pin all those together and show that we get this rapid decrease. So that's for this term starting off no bigger than some constant, some universal constant, yeah.
Why is the dimension popping up in the norm of the action? Is it because of the choice of the norm, or?
It's because of this working with. Yeah, it arises because we're keeping track of the Frobenius norm here, and we start out with identities, right? With a.
Why do you need Frobenius norm?
What was your question?
Why are we working in the Frobenius norm? Yeah. Yeah, because I guess we don't know how to do it any other way. This is
Possibly.
that's where the D arises. Is it essential? I don't know. Yeah. Yeah. Question. Okay, so that's if we're thinking about that's the general case that has this condition that, you know, as long as our loss is not too big, then things work nicely. But you know, perhaps we shouldn't be surprised by that because we should expect things to be locally nicely behaved. I mean, I guess that's not true in the sense that you know, there's something surprising there because we have a continuum of solutions, right? At any point in this theta space, we can move around and compute exactly the same function, right? Because you can rescale things to do things in that way. But this doesn't hurt, I guess, is the message of that analysis. Okay, if we want to say something that's stronger, that's, you know, about a whole set of linear maps that are not necessarily starting off suitably close to the optimum, we need to work with a kind of positivity condition. So let's start with an easier case here, which is symmetric matrices. So our linear map has this special property that it's the least squares, at least. It has this special property that if it's phi times x, then this matrix phi is symmetric. We're going to consider positive definite matrices. So we'll, you know, define this positivity condition that for all unit length u transpose AU is bigger than some number gamma that's greater than 1, greater than 0, and so our, you know, the matrix A is computing a transformation that leaves things at an acute angle to the starting vector. And the theorem is if we work with a symmetric linear map, then you know, if the matrix phi satisfies this positivity condition, the depth here, L, the number of linear functions in our composition is not too small, our step size is not too big, then after, you know, some number of iterations, we get a loss that's less than epsilon. This quadratic thing is less than epsilon. Okay, so for the symmetric case, you know, under this positivity condition, we can reach the optimum using just straight gradient descent. Okay, so actually, if we consider the symmetric case and remove the positivity condition, so come up with just a single negative eigenvalue, and the depth is even, makes the analysis a lot simpler, then gradient descent can never get to the optimum, right? So we're bounded away from the optimal value. This L is the Euclidean norm squared of the product of the thetas times x minus the least squares map phi times x. Okay, so in the symmetric case, we need some sort of positivity condition for things to work, and under the positivity condition, we can get that just a simple gradient descent works. And actually, the negative condition we can extend to a family of regularized algorithms, and I'll put that in fine print, and I'll tell you something about what those algorithms are in a moment. Okay, so in the symmetric case, things are really simple. The idea is just that, you know, everything becomes diagonal. That everything decomposes. So if you've got a set of symmetric matrices, we say it's commuting normal if you can find a single unitary transformation that makes every matrix in that set diagonal. Right? U transpose AU is diagonal for all A in the set. And we start out with such a set, right, because we've got a single symmetric matrix phi, and all of these initial matrices are the identity. So that's clearly commuting normal, right? Because we just need to decompose, do a spectral decomposition of this guy, and that works for I for sure. And then the gradient updates don't mess with that. So you keep things in this setting where everything can be simultaneously diagonalized. So everything decomposes into just what happens on those diagonal entries. They're all independent. It's a sort of funny nonlinear evolution of these diagonal entries, of these eigenvalues. But you can work with those and show that you get the convergent result for these guys. And then in the second part, you can show that you can't get to a negative eigenvalue with an even value of L. So the positivity condition is essential. Okay, and the last part is looking at what happens when we stray away from the symmetric case but keep the positivity condition. Right, so we have positivity condition with this gamma. Then there's some algorithm that after not too many iterations produces a near optimal solution. It's a power projection algorithm, so it's doing a sort of regularization that's keeping things close to the identity. And just to sketch what it does, you're taking a gradient step for each of the parameter matrices. You're projecting the product of those onto the set of positive matrices, a set of matrices that have this margin gamma, right? And then you're setting the subsequent parameters to be a certain factorization of that product, and it's a balanced factorization. So you're spreading out the scale of all of these, spreading out the scale of this transformation evenly across all of those parameters. And what's this balanced factorization? So it turns out you can write any matrix with a particular set of singular values as a product of matrices that all have the same singular values. They're kind of the 1/Lth power of these singular values. So the scaling happens is spread out evenly across these L matrices. So and you can write that explicitly by computing a polar decomposition, right? A unitary matrix times a positive semi-definite matrix, and then everybody's got sort of an equal contribution to the scaling part of that transformation. Right? So if you do things in this way, you can think of that as we're taking a gradient step and then we're projecting onto a certain set and making sure that the linear transformations at each step all have a similar scale, all have the same scale. Okay, that's the intuition in that case. All right, I should stop there. So just to summarize that, for the second part of the talk, gradient descent, converges if we've got a sufficiently small starting point with these identity maps. If we've got a positive symmetric map, we get a convergence result there. Without the positivity condition, for the symmetric case, we certainly don't get convergence. And if you regularize to keep things close to the identity, then you can, again, with this positivity condition, then you can show that things work there. And we're getting this exponential convergence in all of these cases. And I guess, big question is what can we do in the nonlinear case? All right, I'll stop there.
So this is a theoretical analysis making the assumption that every layer is close to linear. Is that something you actually observed in trained ResNets? Did you compute the operator norm of every layer and observe that the norm was closer to the identity when you had more layers?
Right. So yeah, I don't know what's been observed experimentally for the nonlinear part in ResNets. Yeah.
Because it used to be the case when we used single-module networks that the knowledge was to initialize the parameters close to 0, exactly to be the linear part.
Right.
So this seems to match.
Right. So you're using a stochastic gradient method. You're starting off with small parameters, but where do you end up? Yeah, I don't know.
Do we know how much statistically we lose? I mean, how large is this class of? So we say
Things that are close to the identity?
Yes.
Yeah. So that was the third part of the talk, which apparently would have taken me over an extra half hour. So we have some analysis that works with the scale of these mappings, right? That works with that you can get a generalization bound that says, the excess risk I suffer depends on an upper bound on how much things get blown up from the input to the output. Right? So if you take an operator norm, if we have a composition of maps that have linear part and a nonlinearity all the way through, if those nonlinearities have some fixed Lipschitz constant, as all the ones that are used in practice do, the ReLU one, max pooling, those sorts of things, then we can get an upper bound on the excess risk in terms of the something like, there are fudge factors, the product of the operator norms of those matrices at each layer. And in the residual net case, you can do a deviation from a fixed matrix like the identity. Yeah. It's sort of a natural notion of scaling. Like by how much can an input vector be blown up when it reaches the output. And if you have constraints on that, then you can give results in terms of that quantity. Yeah.
Would that sort of theoretically deteriorate with deeper networks? Since you can blow things up more?
Right. So that's a good question. So you get a product of these operator norms. So these things are getting bigger and bigger as the depth increases. You can impose extra assumptions and get something that has. So there are fudge factors in there. You get this product together with some other thing, and in general, those things could grow exponentially with the depth of the network. You can escape that sort of growth. So Sasha has some results with Noah Golovich and Ohad Shamir. That improves on something I was going to present. In some special cases, in terms of the dependence on depth. Other questions?
Thank you.
All right.